Okay, so remember we had got to this stage where our exponential distribution had been fitted to the data in this way. You can see it looks like this part of the graph ought to be a nice exponential distribution, but it doesn't fit too well really, because it's trying to fit this part of the distribution, which doesn't work very well, with this part of the distribution, which would work quite well. So let's look at what part of the distribution we're expecting to be exponential, then see if we can fit this exponential distribution to this graph rather better. So at this sort of point here, about point 14, it seems from then on it seems to be pretty reasonable. So let's just take out the data up to that point, or at least take out the root mean square up to that point. So remember that was our proportionate frequency. That was the number of our data values which were between 0 and 1 divided by the total number of data values. That was the value we get from the exponential distribution with our parameter that we've worked out, 0.00936, and that's the square root of the difference. So if we want to ignore the first 14 data points and fit the rest of the graph to it, what we can do very simply is replace this squared difference for the first 14 points with 0. I'm just going to save the spreadsheet first. Should always do that before making a significant change. So I'm going to put 0 in there and drag that down to the first 14 data points. Okay. Now we need to reconduct our experiment effectively and see how we can minimize the root mean square difference. So the root mean square difference there is now 0.000477, but that's with our lambda of 0.00936. So let's just try a wide range of lambdas. Let's go from 0 to 1 in steps of 0.01 and click the optimize lambda button, and off we go. Now we can see, if we plot a graph of this, we should be able to, and that is really rather bizarre. So something's clearly gone wrong here. Let's just take that graph out, and we can see, we just look at this data, get a rather bizarre shape of graph. So if I look at individual values of lambda, say I look at 0.1, you can see that's way out, the graph's way out. So I go back and look at something closer to what worked before. You can see it's a similar sort of graph as I've got before, and I'm hoping to get this slightly steeper. So I'm probably looking at lambda that goes up to, say, there, 0.014. I see that doesn't quite cut it, as it's above the level of the graph. And what I've done here is I've made quite an interesting mistake. By setting these to 0, I've reduced the overall amount of the distribution. So I need to actually effectively set all these to 0, and therefore reduce the total size of the total number of the distribution, as I've taken out some of the frequency. That's why the graph there is not working. So what I'm going to do now is make that change, And I'm going to set these values to 0 down to there. So I set all them to 0, and now you can see immediately my fit's looking a lot better, because the area under the graph is adding up to 1, which will always be the case with the exponential distribution. So now I want to look at, say, if I try 0.015, that might get, well, it gets me a bit closer. But let's try running the optimizer again. So I'm going to go from 0.01 to 0.02 in steps of 0.0001. So I'm going to do 100 of them. Let's get rid of that. And off we go. And you can see how the graph moved there. And let's see where the minimum value was. Well, interestingly, we've actually gone over. The minimum value was actually before, or it's about at 0.01. So let's try that again. 0.005, say, and so now let's have a look at this graph to see if we can get a clear minimum. And we can see we have now got a clear minimum at 0.0103. So we try and refine this. 0.01, 0.011, and let's put an extra 0 in there so we can make it really accurate. And we'll draw a graph of that. And you can see again 0.01026 there. So if we try and plot this between 0.0101 and 0.0103, then we might get a slightly more accurate graph. 0.0101, 0.0104, shall we try? And let's really go for it. So this is going to take a little bit longer because we've tried to do it much more accurately this time. You can see the graph very imperceptibly moving. The root mean square calculation is hardly changing, so it's not making a huge amount of difference. It's probably slightly overkilling the accuracy, but let's see where we've got to. Okay, so lowest there is 0.010247. 10. I need to increase the accuracy of this column to see what's going on. And we can actually see the minimum value here. So it's come down there and starts going back up again. So 0.010241. Let's just copy that value and we'll put it back in there. And there you can see that's the closest we can get. So it's still not an ideal distribution. We're clearly missing some aspects up here, but we are closer to our root mean square average. If I can move that out of the way. So remember we're about 0.002 before, we're now 0.0004. So we're about a fifth of the error that we had before by cutting out that early part of the distribution. So that shows how we can get a bit closer to our distribution by cutting different parts out. But what I'm going to look at now is to go back to the original graph with this full data in and try and fit a 2-parameter distribution to it.